So I lead the algorithms engineering team at Netflix, and today I'm going to give a different kind of talk, very practical. We've been hearing a lot, and we'll be hearing in the next few days about when it makes sense to take in more data, build some smart algorithms to either work on that data at larger scale or make it go faster. I'm going to be giving you a slightly different sort of like approach into figuring out when that makes sense and when that maybe doesn't make sense. So my talk, in the best case, is going to be thought-provoking. In the worst case, it's going to be controversial. But I'm also looking for some of that and some of your feedback on what you think in the way that, from a practical standpoint, we are addressing big data and scalability of algorithms at Netflix. So, and I think it's obvious from my T-shirt and my starting slide what's my favorite original show at Netflix, House of Cards. And I'm going to move on to, I'm going to be, by the way, they told me that I have a little bit over 30 minutes. That's good to know. Introduction, I'm going to be talking about some of the algorithms that we use, and then how do we think about distributing and parallelizing. I use distribute and parallelizing loosely here. I'll mention whenever it makes sense to explicitly distinguish both terms. And I'll talk about one particular example, which is how we distribute neural networks using GPUs and the Amazon public cloud. Okay, so I'm guessing many of the people in the room remember the Netflix prize. That was 2006 when we published a data set and we asked people, can you improve our recommendation algorithms, right? Of course, you can't ask this kind of question in such a way. You need to figure out some metric that can be crisp and can be measured in a way that it's addressable by a bunch of teams and a lot of people around the world. So we decided to go with predicted rating and the root mean square error of predicted rating and we gave 100 million ratings, and you were expected to predict a few more ratings, like around 6 ratings per user, using that data set. At that point in time, that was almost big data, right, in 2006. Of course, this is very small data set. And as a matter of fact, as I'll mention later, one of the issues we came across when we try to use some of the results from the Netflix prize is that they wouldn't scale into our production systems. But in 3 years, which is not a short time, we did manage to get somebody to beat the 10% in root mean square error, RMSE, and we had a winner. Now, if I fast forward from 2006 or even 2009 to today, the world is very different, and Netflix is not an exception. We've moved from being a DVD by mail company to now being a worldwide streaming company, and we have millions of users across the world. We are interested in a different kind of product, which is streaming instead of DVD. Now, from the perspective of the algorithms, that has a lot of, has a big importance. If you think about what people used to do in 2006 in a DVD world, they would put a lot of thought into figuring out what DVD they wanted to get in 2 days, and maybe it was that DVD that they were going to watch with the whole family, and once they got it, if the movie was not good, they had a lot of incentive to go back to the system and rate it and say, hey, this was really bad. Don't ever recommend me something like this again. Now, nowadays in the world of streaming, instant watching, right, what people do, they'll hit play, they don't like something, they'll just go to the next thing. And the incentive they have to give us explicit feedback is much less. So the kind of data has changed, the dimensionality of the data has changed, and the algorithms that we use have also changed. And I'll give you first a taste of what the Netflix scale means and how that's actually the hour stream over different quarters. What we're talking about when we're talking about number of data points. So we have 44 or over 44 million members in over 40 countries. We have more than 1,000 different device types. Then the last public data point that we gave, it's 5 billion hours in Q3 of 2013. And obviously, every hour of consumption, it's a lot of data that we get not only what the user played, but actually where it was played, when it was stopped, from what device, in what location, at what time, and so on. All of that goes into our algorithms. And if you translate those billion hours into plays, roughly it's 50 million a day. We get 3 million searches a day, we get 5 million ratings a day, and we log of the order of 100 billion events every day. And of course, this is publicly known. We are responsible for over 1/3 of the peak internet traffic in the US. And this is what's represented in that graphic over there. So what kind of algorithms do we use? And when I talk about parallelizing and distributing, this is a non-exhaustive list of things that we use in different places currently in production. We use regression models, different tree ensembles, random forest, gradient boosted decision trees, SVD and other matrix factorization algorithms, restricted Boltzmann machines. Those come from the Netflix prize. Markov chain clusterings from k-means to HDP and other non-parametric Bayesian models, deep neural nets, LDA, association rules, and so on. So there's way more than rating prediction and matrix factorization behind the Netflix algorithms. Sometimes people refer to matrix factorization as the Netflix approach to algorithms, and we have way more than that. Where do we use these algorithms? So just to give you, again, a taste, we use them everywhere in our service. This is a headline that I think is kind of very interesting, and it summarizes what we think about our algorithms. We were doing an A/B test that actually was rolled out into being a production feature in a very sensitive part of our UI, which is called the list. The list is a place where users actually store and save what they want to watch next. Previously, we had a similar feature where we allowed users to actually sort things themselves, and you could actually promote something to the top, then sort something to the bottom, and do whatever you wanted. And we said, you know what, let's forget about that. Let's sort with our algorithms that list. Instead of letting the users sort themselves, let's sort it ourselves. We did that, we put an algorithm there, and guess what? The consumption went way up from that list. So even what users do themselves, we can do it much better. Of course, we still allow some users, if they want, because they're very picky and they want to continue sorting the list themselves, they can still do it. But the algorithms are much better optimizing even what users themselves have selected. So we do rating prediction, of course. This is one of our most well-known algorithms, but it's lost a lot of importance recently because of what I was mentioning before. We get much less ratings and they're fewer quality, but we still use it in many different places, not only as a way to recommend, but actually as a way to explain why we're recommending something. We're recommending you this and we're telling you, hey, our best guest is 4.5 stars. What do we use in production? So interestingly, we use the result of the 2007 Progress Prize. For some of you that are familiar, there were 2 basic winners, even after the final 2009 prize. But after the first year, people were using variation of matrix factorization or SVD. That was the stochastic gradient descent approach to matrix factorization that was published in one of the blog posts by the so-called Simon Funk. And then restricted Boltzmann machines that was published by some of Hinton's students in the context of the Netflix prize. So those 2 in isolation had a root mean square error 0.89, 14, 0.89, 90, and a linear blend had 0.88 on the testing set for the Netflix prize. They're currently used as part of production, and we had to do a bunch of work to get them to work. Among other things, the code that we got from the teams back then was only designed for 100 million ratings. It wasn't designed to take in new ratings as they were coming in, so we had to scale it, we had to do some work to productionize it. But they've been in production and they are still in production, and they're the base for our rating prediction algorithm. Okay, but other things we work on with all that list of algorithms, a very important thing that we work on is ranking. We have different learning to rank approaches, because if you think about our UI and what we present in our UI, it's actually a set of different movies in the list sorted by some algorithm, right? And this is the personalized learning to rank approach. Another thing we do is algorithms for page composition. Things here start getting a little bit more tricky. Now we're not only interested in sorting this list here, we actually want to optimize a two-dimensional grid and using some kind of attention models of what users tend to do on that page. And of course, we know whether they're going to be focusing their attention here or they're going to be scrolling on that list or they're going to be scrolling down. Using those attention models, we try to optimize our algorithm for what we want to present. And this is not only about optimizing relevant, of course. There's many different things that go in here, like, for example, diversity. Other algorithms we work on, large-scale similarity, and we use similarity in many different places, like there's some rows that are actually generated by similarity because you watch whatever, what was that, Family Guy, you get these recommendations, or when you search for something, you can also get similar titles. So similarity is something that we also, similarity algorithm, something that we work on. I mentioned search. We do a lot of search recommendations. Most of what people search for on Netflix is things we don't have, of course, because our catalog is reduced, and people usually search for that thing that is on the theater right now, and they want to find it on Netflix. It's not there, but we take that opportunity to recommend things. Or people will search for Italy. Italy is not really a name of a movie, right? It's a concept, or it's a city, and sorry, a country, and we want to recommend things that are somehow related to Italy. What else? We do a lot of different algorithms, smaller algorithms that are sort of like in different places of our UI. Post-play is one of them. You finish playing something, what should be the next thing that we recommend for you to play after that? So all the list of algorithms that I mentioned before go into the experience in some of these places. Okay, so, oh, and I forgot the last one, gamification. We also have, this is only available in PS3 for now, but we have an entertaining game-like experience that is driven by algorithms also. So how do we think about distributing those machine learning algorithms in practice? And when I say distributing, I mean distributing or parallelizing. These are the three main questions that we ask ourselves, and I think it's interesting to just put them out there because I think they're interesting questions that anyone should ask whenever approaching a problem that requires big data and machine learning algorithms. The first question is, do I really need all that data? The second question is, at what level do I need to distribute and parallelize? And the third question is, what latency can I afford? I'll go into these three questions. So the first one, do I really need all that data? So early on in the Netflix prize, there was this blog post where you could read more data usually beats better algorithms. The summary here was there was a bunch of students at Stanford that use metadata from IMDb about the movies. That means like the actor, director, the description of the movie, and they added to the public Netflix data set that was only made of ratings, and they claimed that using that they were getting much better results than other fancier algorithms. So you could say, well, maybe it's all about just adding more features, right? Unfortunately, or not, a few years later, that was after the Netflix prize, there was this paper by some of the people in one of the two leading Netflix prize teams where they said recommending new movies, even a few ratings are more valuable than metadata. So they basically proved that with the right algorithm tuned to the ratings, you could throw in as much data as you wanted, and that they were also using IMDb kind of data, so basically the same one from that blog post, that they couldn't improve the accuracy of the rating prediction. So sometimes you can increase your feature space and you can increase the dimensionality of your feature space, but you're not going to beat a well-tuned algorithm on a subset of the data. And of course, some people will say, well, that's okay, but what about not increasing the number of dimensions in your feature space? What about just increasing the number of samples? And I think most of you will be familiar with the Banco and Brill paper from 2001, where they were showing this famous curve here, where it didn't really matter what kind of algorithm you were using, right? You could use a perceptron or a naive Bayes or whatever. What really mattered here is the millions of words you were using to train your model, and the accuracy basically followed the same pattern. And this, and Norvig saying that Google does not have better algorithms, it only has more data, so makes us think that in many cases, just throwing in more data, it's going to work, and we don't need to worry too much about how do we tune the algorithm. Now, in some cases, that's true, and in language models like this, where you have low bias models with a hugely dimensional space, as many of vocabulary words you have in your vocabulary, that will be true. But in other cases, that doesn't work this way. Here is a graph from one of the models that we have in production at Netflix. And here you have the number of training examples in millions. And you can see that roughly after, around 3 million training examples, the curve is basically flat. This is the testing accuracy. And what testing metric we're using doesn't really matter because it's the same for most of the metrics that you can think about. But what matters here is that after 3 million ratings, we've basically just saturated the model, and it doesn't really matter, right? And of course, that depends on what dimensionality you're using and whether you've been able to reduce that dimensionality using some unsupervised approach, for example, like the matrix factorization approach that I was mentioning before, or some clustering technique, or something like that. So, yes, sometimes it's not about adding more data. So the first question you should ask yourself when you have a big data problem is like, do I really need all that data? The next question that I was mentioning before is, at what level should I parallelize or distribute? I talk about the 3 different levels of distribution, and the first level is for a subset of the population. The second level is for a combination of the hyperparameters, and the third level is for a subset of the training data. And each of the levels where we parallelize or redistribute has a different set of requirements. And if this is not clear now, I'll try to make it clear in the next slides. So level 1 distribution. We may have subsets of our population. I'm using population in the broad term of a statistical sense of like, but it could be really population of users. In our case, it could be users, but it could be items or anything. We can train maybe independent optimized models for those subset of the population, right? So in our case, in Netflix, and in many cases of sort of like internet companies, it's clear. You could train an optimized model for the US, an optimized model for the UK, an optimized model for France. You have completely distributed learning training algorithms. They don't need to communicate whatsoever. And this could be a way to approach what I call the level 1 distribution. Of course, here we don't need to do much, right? But this could solve one part of your distribution problem. Second level. Now, the second level, things start getting a little bit trickier. Now, for each of those regions, you need to optimize a set of hyperparameters, right? That's always, or most of the, in most cases, you'll have some hyperparameters, your regularization, lambda, you'll have to tune the number of layers in your neural network, you'll have to do whatever. And that needs to be using the same kind of, the same training data from a subset of your population. Now, we can do that. In the worst case, you can do a grid search, of course, but you can do much better than that. You can use some kind of Bayesian approach using Gaussian process priors. And this is something that does require some coordination. And the coordination that requires is what is going to be your next iteration of the optimization for the hyperparameters, right? You launch a combination of your hyperparameter settings, you see the results, and you need to decide what is going to be your next step and where are you going to explore your space of hyperparameters. And this requires data distribution, but it doesn't really require data sharing so much, right? You could have distributed data for each node, train a model, get back with the results, and then go to the next iteration on the hyperparameter optimization. And the third level of distribution or parallelization is where you really need to do for a single training algorithm on a set of hyperparameters, where you need to do some kind of breaking your process into different machines or into different cores if you're doing parallelization, right? Here, you do require coordination and data sharing, and you can distribute computation over several machines using ADMM over parameters or over examples, or you could also parallelize, and that's other approaches that we hear about, parallelize on a single multi-core machine using approaches such as Hawk-Wile, which are very interesting for things like matrix factorization. And yet, a third approach is you could use GPUs. And this is basically what we did here in our neural net training over GPUs and the cloud. So here, the way we address the three levels of distribution is by basically having level 1 distribution, which is the algorithm itself, the training of a single neural net configuration with a set of hyperparameters on a single machine, of course, over hundreds of cores in a GPU. Now, when we had to do the level 2 optimization, level 2 distribution, and we had to learn the several hyperparameters, we did that in the cloud over several machines. So basically the idea is you launch several machines, each one with thousands of cores on GPUs, you optimize for those hyperparameters, and you get back the results, and you go back to the next iteration. We were doing this on a central node, which was, in our case, it was running Spearmint plus Condor, but you can use a different number of combinations of different, actually I have it here, like Condor, Star Cluster. We're currently now exploring with using Mesos also as a clustering coordination mechanism. So again, level 1 distribution, machines over different AWS, Amazon cloud regions. Level 2 distribution, different machines in one region using some kind of coordination tool like Spearmint for Bayesian optimization and some kind of clustering coordination mechanism. And then level 3, which is not distribution now, it's parallelization over highly optimized CUDA code on GPUs. So again, the three questions were, do I need more data? What level should I distribute? And the last one is, what latency can I afford? So this is how we think about any machine learning system at Netflix. And I think this is how we think about many machine learning systems in most of our internet companies. We have offline processes, things like Hadoop, that build models, train models. They do a lot of stuff. They don't really need, they can have a high latency. They can work for a day, for example, even more. And we don't have really any strong latency requirements. Then we have the online world. And the online world is where we have the strong SLA and latency requirements, because the user is there and we want to compute something in a few milliseconds in order to give the response back. And then we have this middle ground here, which is really interesting, where we can have things computed in a matter of minutes or seconds in response to user events, but we're not presenting them right away when they happen, right? And how we distribute the different algorithms on these three layers and what kind of latency we can afford is really important also in defining our distribution or parallelization strategy. Just to give you an example, going back to the matrix factorization example, if you think about how we decompose a matrix into, in the traditional Netflix case, you have an item vector matrix, which is DM, and a user factor matrix, which is the U. Now, traditionally, you would want to optimize and to solve the equation for both matrices at the same time, and that's what's usually done if you're in a purely offline setting. But that's not necessary, and there are better ways to do it. Actually, one interesting thing that you can do is compute your item factors offline. Just take as much time as you want, or maybe subsample your data for whatever number of latent factors you think, or for however many samples you need to identify your latent factors, and then compute your user factors online. And actually, this is a least square equation that you can solve with modern libraries in a few milliseconds. So you can really do the user factors, solve this equation, and use it for something like rating prediction or ranking or whatever you want in an online fashion, as long as you've solved these item factors in an offline way, right? So again, how much data do I need? What level do I need to distribute or parallelize? And the last question is, how much latency can I afford? And how can I break my algorithm in ways that I can do some of it offline, and whatever needs to be done online, I can do it in a much faster way. Okay, so I think I'm done, and I did take a few more minutes, but thank you very much.